Welcome to The Explainer. Today, we are exploring the invisible machinery that literally powers all of our devices. As developers, we get to write code using these highly readable, almost conversational commands, right? Things like print or download. But here's the catch. A CPU? It only understands raw binary machine instructions, zeros and ones. So the absolute fundamental challenge of computer science is bridging this massive gap. So I want you to think about this for a second. How does a simple text string, something as basic as hello world, actually force physical microscopic transistors to fire in a highly specific sequence just to light up the pixels on your screen? It's crazy when you think about it. It's this incredibly complex translation journey, and it's happening billions of times a second on the very device you're watching this on right now. Okay, let's dive into this. The absolute golden rule of software is that all source code must be translated before execution. No exceptions. A command like print hello absolutely has to transform into a raw binary string. Without this translation step, your code is literally just a dumb text file. Programming languages simply do not run directly on bare metal hardware. Before anything can execute, it must be translated. And historically, the computer science world has been split into two major camps for handling this translation: compilation and interpretation. So the first major approach is ahead-of-time compilation, or AOT. Think of your heavy hitters here, languages like C, C++, Rust, or Go. In this model, you write out your source code, and then a dedicated program, called a compiler, takes that entire code base and translates the whole shebang into machine code all at once. And this happens before you even attempt to run it. The resulting executable program can then be fed directly to the CPU. The massive, undeniable advantage here: extreme execution speed. Compilers can actually spend time optimizing your code, doing clever things like loop unrolling or function inlining. This means the final machine code runs blazingly fast. But the downside, that initial build step can be agonizingly slow. You have to wait for the compiler to completely finish its job before you can even test your program. Let's move to and see how this builds on the direct alternative, which is interpretation. Think of languages like Ruby or, historically, JavaScript and Python. Instead of translating everything up front, an interpreter executes the code line by line, right there during runtime. It reads a line, translates it to machine instructions, executes it immediately, and then moves right along to the next line. This allows for incredibly fast development cycles, because you just write your code and hit run. Boom. There's no waiting around for a compiler. But there is a massive performance penalty here. Imagine a loop that runs, say, 1 billion times. The interpreter has to read, parse, and translate that exact same piece of code 1 billion times over. That adds some serious overhead during runtime. To really anchor these technical concepts, imagine translating a speech. Compilation is kind of like taking a foreign language speech and translating it entirely into a printed book beforehand. When it's finally time to deliver it, you just read smoothly and quickly straight from the book. It's perfectly optimized, ready to go. Interpretation, on the other hand, is much more like a live translator at the United Nations. They translate sentence by sentence as the speaker is actually talking. Now, this is incredibly flexible, right? If the speaker changes their mind and goes completely off script, the live translator can instantly adapt. But overall, the entire delivery of the speech takes significantly longer because of all that real-time translation overhead. Software engineering is always a battle of trade-offs. Compiled programs, they clearly win on raw execution speed and instant startup time, hands down. But they lose big time on portability. A compiled Windows executable simply will not run on a Mac or a Linux machine. That machine code is intimately, structurally tied to the specific operating system and processor architecture. Interpreted languages, however, are highly portable. As long as a given machine has the right interpreter installed, your exact same source code can run absolutely anywhere. So it's the classic trade-off. Do you want the rigid, blazing speed of compilation or the slow but incredibly easy flexibility of interpretation? For decades, developers basically had to pick a side. You had to choose one or the other. But then came a massive architectural breakthrough. The hero of our story, just-in-time, or JIT compilation. JIT is this advanced, hybrid runtime model designed to basically give us the best of both worlds. It's the absolute secret sauce behind the Java virtual machine and modern JavaScript engines like V8, which, by the way, is what powers Google Chrome and Node.js. JIT systems don't force you to choose between slow flexibility and rigid speed. Instead, they dynamically combine them right in the middle of execution. Now, what's really interesting about this slide is how it breaks down the JIT process. When you run a JIT-powered program, it actually starts out behaving just like an interpreter. It reads intermediate bytecode, so it can start up almost instantly. But as it runs, the runtime acts like a very observant live translator. It actively monitors the execution and detects what we call hot code. These are the specific loops or functions that are being executed repeatedly. Once it identifies a hot path, the JIT engine secretly, in the background, compiles just that specific piece of code into highly optimized native machine code on the fly. So the next time the program hits that loop, it completely skips the slow interpreter and jumps straight to the lightning-fast machine code. And this leads us to a fascinating phenomenon that's entirely unique to JIT systems: the warm-up phase. A JIT application actually starts off relatively slow, simply because it's relying on standard interpretation at first. But as it gathers execution statistics and begins applying these adaptive optimizations to the hot code, the execution time drops dramatically. The longer the program runs, the faster and more efficient it becomes. It is literally learning and optimizing its own performance in real time. How cool is that? Okay, now I want to introduce a bit of a narrative twist here, something that kind of challenges everything we've just covered. We know that interpreted languages suffer from major runtime overhead, right? They are mathematically, demonstrably slower. We also know that artificial intelligence and data science require massive, mind-boggling amounts of mathematical computation. So, here's the paradox. Why is Python, a notoriously slow interpreted language, the undisputed king of heavy-duty AI and machine learning? It doesn't seem to make any sense. Well, the secret to this magic trick is that Python isn't actually doing the heavy math itself. Not at all. In the AI world, Python acts merely as a highly productive orchestration layer. When you're using tools like NumPy, PyTorch, or TensorFlow, sure, you are typing Python code. You're taking full advantage of its fast development speed and super easy debugging. But underneath the surface, your Python code is really just passing instructions down to lightning-fast, highly optimized, pre-compiled C and C++ libraries. Python is simply the conductor pointing the baton. The actual heavy lifting is being executed by AOT-compiled C++. So you get the amazing developer experience of an interpreted language paired with the raw execution speed of a compiled one. So the crucial point is, why do we care so deeply about all of this? Why spend decades, literally decades, inventing incredibly complex architectures like JIT engines or hybrid AI orchestration layers? Well, because at a macro scale, execution performance fundamentally dictates reality. Code performance directly affects how a product scales. It dictates your massive infrastructure and cloud computing costs. For mobile users, an inefficient interpreter literally drains the physical battery right out of their pocket faster. It impacts user experience, it impacts latency. The translation gap between human text and machine code genuinely governs the efficiency of the entire digital world. And this brilliantly illustrates exactly what is at stake here. Saving just one single millisecond of execution time per request might seem totally meaningless to a human being. I mean, it's a fraction of a blink of an eye. But if you are a major tech company and you're processing billions of requests a day, that single optimized millisecond compounds. It translates to requiring fewer physical server racks, using fewer megawatts of electricity, and ultimately saving massive, massive amounts of money and infrastructure costs. It is exactly why tech giants pour billions of dollars into squeezing every last possible drop of performance out of their compilers and JIT runtimes. We've journeyed all the way from the rigid, pre-planned speed of ahead-of-time compilation to the flexible but slower nature of interpreters, right up to the absolute genius, adaptive learning of just-in-time hybrid systems. And as we continue to innovate, we are left with a lingering question. Will the runtimes of tomorrow finally erase the line between human flexibility and machine speed? Are we eventually going to reach a point where we have absolutely zero compromise? It's a thrilling frontier in computer science. I really hope this explainer has given you a much deeper appreciation for the invisible, real-time magic that is happening inside your CPU right now. Thanks for joining me on this deep dive into the architecture of code